We've talked about the importance of magnetic fields in electronics, but with an EM relay, we use electromagnetism to our advantage by turning it into a switch that doesn't require human operation. So, what is an electromagnetic relay? Well, it's an electrically operated switch that uses an electromagnet to open or close a circuit. A relay is primarily made up of a coil, that's the electromagnet, which creates a magnetic field that moves the actual contacts, the switch, which turns the circuit on or off, along with there being an armature and springs. No current in the coil puts it in the default state, and current in the coil puts the opposite state. A small current can control a larger current. Think kind of a precursor to types of vacuum tubes and transistors. Can also isolate two parts of a circuit from each other. You've got a control signal and you've got the main signal. Think of it something like similar in vein to a transformer, although we will be covering that in a future video. They're used for a number of things: automotive starters, industrial control panels, some home appliances, alarm systems, and power protection systems. They can work pretty well with low power MCUs because they allow MCUs to switch much heavier loads. Also, electromagnetic relays dominated electronic pinball machines from 1947 to as late as 1976, 1977, as their relatively slow response times were perfectly fine for pinball machines. They can come either normally open or normally closed. Keep in mind, these are still switches. They still have throws and pulls, single pole, single throw, if you remember from our introduction to switches video. Now, in real life, a relay engages at about 70 to 80% of the rated voltage and disengages at about 10 to 30%, allowing for a certain amount of hysteresis. Now, there were electromagnetic relay computers, or actually still are, but EM relays that can be used to implement logic gates, memory elements such as flip-flops or shift registers, counters, various arithmetic circuits. The Model K, built in 1937, it's called K because it was literally built on a kitchen table, proved that the relay could be used for 1-bit computation. This paved the way for EM relay computers later. 4 years later, the Z3, arguably the first operational programmable digital computer, used almost 3,000 relays. A couple of years later, the Harvard Mark I that used 3,500 relays and over 750,000 electromagnetic parts. You had the Bell Lab Model 2 relay calculator about the same time that used approximately 440 standard telephone relays. The important part of that is that it was using pre-existing relays used for telephone switching. Now, the downside of this is that switching times are extremely low, literally measured in milliseconds, while vacuum tubes are in microseconds, and transistors started in hundreds of nanoseconds, and in some cases now are a fraction of a nanosecond. There are a number of modern built EM relay computers, basically built for demonstration purposes. It's kind of one of those hot things that's been done over the last 20 years. RC3, Diviac 1, Mercia, Suzy. There's some others. A number of people are well known as experts in the field. Now, what type of options are out there for hobbyists? Well, keep in mind that raw EM relays really aren't built for breadboards. They may fit, but they'll probably be pretty loose. They probably won't make good contact with the contacts, but again, it might still work. I've put down a list of some models here, including some that I have. They definitely vary by quite a bit. The examples here are single pole, double throw, double pole, double throw. You can get even bigger ones that will operate a number of different circuits. There's also relay modules that you can buy. They can be a little bit more, but they'll come with screw terminals. They're available in both the normally open and normally closed. um, single pole, double throw, whatever configuration you need. And on top of that, they often come with things like an optocoupler that further helps to isolate the circuit. So, with all their inherent limitations, why would you still use them today? Well, I mean, obviously, you can use them for demonstrative educational purposes, but they're good for switching high power loads. Relays can often handle better isolation in terms of electrical circuits. There's not the polarity issues with AC. They can very easily handle mains AC. And usually there's no need for heat sinks either. Um, Simple logic and control circuits, they've already been used for that. They've been used for that for nearly a century. Um, Automation systems, this can go from the idea of switching high power loads and well beyond the hobby level, agricultural and industrial purposes. Restoration, I mean, if you're restoring old pinball or arcade machines that use these, there's a use right there. Relay computers, you can make them on a smaller scale or you can make them on a bigger scale. Again, not really practical, but it is one of those things that have been made for the last 20 something years. You really need to isolate signals, really physically isolate them, such as with audio signals. This can be incredibly useful. Good for safety systems where the signals absolutely have to be isolated, no questions asked. Emergency shutoffs, fail safes, control systems. Lastly, some DIY measurement and test rigs, for range switching, multiplexing, calibration switching. All right, let's go back to every circuit and let's look at what our relay option is. All right, we got a relay. It allows us to set and operate and a release value. The default is 3.5 and 0.25 respectively. Those aren't bad ranges actually for something that's meant to operate at 5 volts. We've got a coil inductance of 100 millihenries. We've got a coil resistance. Now a real coil would have all these effects because we're still dealing with a magnetic coil. We've got some contact resistance. I'm not sure to the degree these numbers are what these numbers would actually represent of a real model, but we're just going to go with something simple. All right. Well, as we go for anything, let's set up power source. Since this is meant to be working with 5 volts, let us set up for 5 volts. Let us, now, how do we want to do this? Do we want to be normally on or normally off? Let's say normally off for this. Let's grab our ground that we always have. Other end. All right. Let's put in a resistor and we're going to put in an LED because so many of our things do. All right, so we got nothing that switches. Okay, so no power. Now you'll notice that it switched to the right side is the magnet isn't pulling it, the coil isn't pulling it. So we're going to need some kind of power source on the other end. Actually, you know what? No, I'll just set it as another power source. Keep it kind of simple. All right, let's set it up. I'll just put the ground to that. We'll start at 1 volt because actually setting at actually, you know what? I'll set it to 0.1 because setting to zero, trying to set to 0 volts on every circuit is very annoying. All right, let's run it. Okay, it's not doing anything. It is sending voltage through here, but not enough to engage the electromagnet. Just keep taking it up. Now we already know what it'll take. 1 volt, 2 volt, 3 volt. Just push it to 4. Okay, it flipped. There was obviously a delay because it's a physical. Actually, wait a minute. Let's turn this down, the resistor. Whoops. Nope, that's not what to do. All right, so lights on. All right. So if we take it below 3.5, what'll happen? Nothing. Okay, the magnetic field's still there and it's still holding the switch. This is normal in real life. We've got hysteresis there, of a form really, because again, it has it has an upper threshold and has a lower threshold, and it's not going to change until it meets one of those thresholds. That's hysteresis right there. All right, bring it down to one even. Okay, well, let's keep bringing it down. Now it should do it when it hits. A nothing yet. Oh, there we go. Snapshot, or I should say released. Bring it back up. Nothing. Gotta take it all the way back up here. Okay, three. No. There we go. Snaps again. Now the question is, what can we do with this? Well, let's start with making an inverter for one. We've got power going through here. We flip a switch, turns off. So yeah, we've got an inverter logic gate. It's a little slow, but it works. Now, what if we did two LEDs with a pulse signal? You don't really have to wonder where that pulse signal is coming from, but yeah, we could use it to switch two lights on and off. Now look what that kind of looks like really. And then the main pulse. Let's see. Now here's Falstad. I've made some adjustments to this relay so it operates a little closer to a real one. There's apparently some limitations with the relay and Falstad. You'd have to make a more complete circuit to simulate it a little better. But let's keep bringing it up. Nothing. More power going through this one circuit. Oh, and it switched. Now let's bring it back down. I've set it so it's not immediately, the thresholds are different. So there's that hysteresis. Will reach a certain point. There we go. And then this is based on current in this case. Let's look at some other examples. Now I haven't made adjustments in those, so let's look at an AND gate. This is a 3-input AND gate. Nope, nope, nope. So we're just doing it at a time. That's going to do it. Do it at a time. That's not doing it. We've got to do all three, and there we go. The OR gate basically is working the same way. Yep, three of them. So OR, as long as one of them is high, the output is high. Let's look at something a little more interesting. Here's a multiplexer. It's a 3 to 8, done with relays here, 3 different levels of relays here. So So 0, 0, 0, or three lows would be the first, or I should say 0, 1, 2, 3, 4, 5, 6, 7, 8. It just moves through it just like any typical multiplexer. Now this isn't set to proper hysteresis or faster switching times. So in real life, this would be a little slower. These more interesting things. We can make a flip-flop with this. Here's an SR latch, not technically a flip-flop because there's not a clock. But yeah, set. We keep doing it. Nope, we have to reset. Doesn't do anything. Set. So yeah, flip-flops could be made with relays before transistors were a thing. And if we can make a D flip-flop with it, we can make a shift register. And there's a toggle one, or T flip-flop, an oscillator. So basically there's a circuit with a capacitor. And the coil is basically an inductor, the coil inside the relay. And we can even have an interesting little counter here. It's using a clock signal, but anything that would provide that kind of signal. So the one on the top here is 1 unit, and then the next one, which is the one displayed on the right, the one in the middle is half, and then the one on the bottom on the left side is a quarter. And this is all handled through series of relays here. All right, here's a little relay setup in CMU IDE. Got a relay in the middle. It's going to turn on at over 20 milliamps. It's going to turn off at 10 milliamps. We've got a little LED, a battery source, a resistor. We're saying we're using a current source in this case. So at 0.01, nothing, 0.02, nothing. We go above that, it turns on. I go down to below 0.1 to turn it off. Pretty instantaneous. In fact, does it actually have a travel time even listed? Oh, reactive step, I think maybe. Actually, all right. All right, so that's basically what it looks like in Simu IDE. Now, just to wrap things up, an electromagnetic relay or EM relay, electrically operated switch that allows an electromagnet to switch a circuit on or off. There's still switches, so all my previous videos on switches still apply. It just happens to be operated by a control signal powering up a coil. So they still can be classified as poles and throws. Normally open versus normally closed, just like with any switch. Really good for circuit isolation. Small current can switch a much larger one. A number of early computers and precursors to computers were made with EM relays, as well as automatic telephone switch banks. There are a number of hobby options. Modules are probably more accessible with additional features such as optocouplers. Keep in mind through all this that switching times are really slow compared to vacuum tubes and transistors. Well, until next time, have a good one.